All right, so let's get back to our proof of prims. We're going to start by just saying that prims creates a spanning tree. All right, so this actually turns out to be fairly simple because it turns out that prims always maintains this invariant that it spans found. So our minimum spanning tree is always going to span the set of found vertices. And you know, this pseudocode I like to use because it sort of is easy to transcribe into programming language. But let me show you this in a slightly simplified version of pseudocode. So here's Prim's algorithm again. We're going to have our found set, and I'll just abbreviate that X, that way I can fit things on the slide easier. We're going to have our minimum spanning tree. We'll call that T. What Prims does, again, is it says, while not every vertex has been found, so while our found set is not equal to the set of all vertices, grab out an edge, U, V, that's the cheapest of all possible edges, where U is in X and V is not in X. So let me show you the picture accompanying this. We have a set X. We have a set that's all the vertices not in X. And we have a start vertex. That's how we start X. So at any given iteration, Prims is going to look at all these crossing edges. The edges that cross the cut from X to V minus X. And it's going to pick the cheapest one. And what does it do? It adds that edge to T, and I'll denote that by putting it in green here. And it adds the vertex that it was connected to X. So in each iteration, what we can say is that T spans X. And that's true the first iteration. And you'll see through this example that it's true each iteration. So the next time through this algorithm, we would pick a different V, and looking again at all these crossing edges. So this one is the one that minimizes things. So we do the same thing again. We bring it over, we add that edge to T, and we add the vertex to X. So T still spans X. And we can do this again. And we do it for every vertex. And we do it for every vertex that that's not yet found. And in this iteration, you'll see that there's an edge here that also crosses the cut, but we don't care about that one. It's a red edge. It doesn't ever belong to the minimum spanning tree, so we do not have a cycle here because that red edge is not part of the minimum spanning tree. Only this UV edge is part of the minimum spanning tree. Two more iterations. And now we have all of our vertices inside X, and we have a spanning tree that spans all of those vertices. So it's a little informal, but I think just by showing you what Prims does each iteration, it's sort of intuitive to say that it's impossible for it not to span the vertices that are inside X. Okay, so the second part is that we need to say that the algorithm is guaranteed to terminate with X equal to V. So that means that it's a spanning tree for the entire graph. And our key here is that we loop until X is equal to V. So that one's also pretty easy to show. So the only trouble here is that the algorithm does not terminate. The only way that this algorithm does not terminate, so the only way that this is an infinite loop, is if we can't find this edge. And the only way that we can't find this edge is if, by the empty cut lemma, the input graph is disconnected. And as part of our assumptions at the beginning, we said that we were operating on connected graphs. So we're always guaranteed to find this edge by the empty cut lemma. All right, we'll also need to check that the set of edges T doesn't contain any cycles. Well, we know it's not going to contain any cycles because we always grab a vertex where one vertex is in X and the other vertex is not in X. And by the no cycle corollary, the addition of this edge cannot create a cycle because it's the only edge to cross the cut that's being included in the minimum spanning tree. Okay, so for Prim's outputting a spanning tree, we've shown that it maintains the invariant that T spans X. We've also showed that it's guaranteed to terminate with X equals to V. The only thing that can go wrong is if we have a disconnected graph. So that's the only circumstances when we don't have that. And by the empty cut lemma, the input graph must be disconnected, but we stated that as an assumption to begin with. All right, and 3, we have that the algorithm is guaranteed to create a tree with no cycles because for any iteration, we add an edge to T, and the edge must be the first edge to cross this cut. And by the no cycle corollary, it cannot be part of a cycle. Okay, so we know that Prim's outputs a spanning tree. The next part here is the minimum part. Do we have an algorithm that gives us the minimum of all spanning trees?